Welcome back. So we left off last time talking about confidence intervals a lot, and p-values a lot. And I said, why have we gone over all of this? And it's because in our test statistics, we don't just want to understand how big the relationship between our independent and dependent variables are. We also want to understand whether they exist in the full population. And to do that, we determine whether or not they're statistically significant, or at what level, what confidence level they are statistically significant. If they are statistically significant, then we can keep going and look into how strong the relationship is. And I said I'll pick up next time by talking about how we can do that. In order to do that, we need to first know the level of measurement of each of our variables, and then we can determine which analytic techniques we should use. So the table you see here gives you a general idea of how that might work, using 4 different test statistics or 4 different measures of association between X and Y. So if your dependent variable is at the interval or ratio level, and again, those are substantively different, but for analysis purposes, we treat them the same. So they are substantively different, but functionally the same. In those cases, when you've got an independent variable that's nominal and has only 2 categories, or ordinal and has only a few categories, then you want to use a t-test. If your dependent variable is interval or ratio and your independent variable is nominal with more than 2 categories, or ordinal with only a few categories, then you want to use ANOVA. These are not, by the way, mutually exclusive. You can do several. If your dependent variable is nominal or ordinal and so is your independent variable, then you'll use the chi-square statistic, and you'll also use some of its extensions, some kind of cross-tabulation, and some more extensive statistics that I'll talk about in a moment here. And if your dependent variable is interval or ratio, and so is your independent variable, then you're going to use pairwise correlation. Okay. So you've got your data, you're ready to test your hypothesis. The first thing you do is present some descriptive statistics and explore your dependent variable. You give us measures of central tendency, you give us range, you give us all the univariate stuff we talked about last week. Then you do that for your independent variable. And then, after you've described your single variables, the next step is to look at whether the 2 theoretically related variables, right, that you connected through your theory, have a statistically significant numeric relationship. The type of test you use to determine this depends on the level of measurement of the variable, right, like we said. So let's say we've got a situation where 2 variables are nominal or ordinal, and we want to know if the relationship between them is more than random, is actually systematic and due to more than chance. You will first create a crosstab of the variables. So you've got one of them in rows with each category in its own row, and the other variable in columns with each category in its own column. You make like a 2x2 or a 2x3 or a 3x3 table or whatever, depending on the number of categories in each of your variables. And then you calculate a measure of association, some measure that shows us how significant or how strong or how meaningful the relationship between the variable in the rows and the variable in the columns is. So here's one where I'm studying movie genre preference by gender, and this is according to ticket sales. So for genre, 1 is rom-coms, 2 is action movies, and 3 is horror movies. For gender here, 0 is male and 1 is female. And then the numbers are just how many tickets were purchased by gender to each of those genres. It's cool, right? To get a crosstab in Stata, you type the word tabulate. You can also abbreviate it, just tab, T-A-B. And then you type the name of your dependent variable. And then you type the name of your independent variable. And then you type a comma. And then you type the measure of association that you want. So for a chi-squared test, you would type tabulate, dependent variable, independent variable, comma, chi2, chi-squared. And you see the crosstab, and at the bottom of the crosstab is your chi-squared statistic, and it has 2 pieces of information. the statistic itself, which I'm not going to go through in this course, and the PR. PR is probability. This is the probability that the relationship is statistically significant. And again, it's a proportion of times out of 100 that the true value is in there. So you take 1 minus that probability. In this case, it's 1 minus 0.041, which is 0.959. So this relationship is statistically significant with 96% confidence. And we want to give it a conventional level. So we're going to say it's statistically significant at the 95% level. All right. After we've determined whether or not there is a statistically significant relationship, and we have found that yes, there is, then we want to know the strength of that relationship. To determine the strength of the relationship, we perform something called a non-parametric test. In the table a couple of slides ago where I mentioned what kinds of bivariate statistics to use, and it said chi-square and extensions, I just covered the chi-square. These are the extensions. There's a whole variety of these non-parametric tests, and they depend on whether your variables are nominal or ordinal, and if nominal, how many categories they have in them. So after we calculate the chi-square test, we need a way to interpret it. For nominal variables, we can use one of 3 different non-parametric tests. We could use phi. Phi is bounded between 0 and 1. That means the lowest this number can be, the statistic can be, is 0, and the highest it can be is 1. If the phi statistic is equal to 0, it tells us that there is no relationship between the 2 variables. If the 2 variables are perfectly related, then phi will equal 1. So phi is going to give you a number between 0 and 1 that tells you how related these two variables are. 0 means not at all. 1 means in every possible way as much as possible. And usually we get a number that's in between. You can use the phi statistic if you have 2 by 2 tables. So if you are testing a hypothesis where your independent variable only has 2 values, where it's binary, and your dependent variable only has 2 values, so that it is binary. If you've got 2 binary variables, one independent, one dependent, then you can look at the phi statistic. Another non-parametric test you might use is the contingency coefficient. You can use this if you have a square table. So an independent variable with 2 categories and a dependent variable with 2, or they both have 3 categories, or they both have 4 categories. As long as the categories are matched in that as long as the variables each have the same number of categories, you can use this. So your crosstab is a square table. The contingency coefficient also is bounded by 0 and 1. So if it is 0, there is no relationship. If it is 1, there is a perfect relationship. Oh, crap. I'm sorry. No, ignore that. The contingency coefficient is not bounded by 0 and 1. Its bounds are going to change depending on the number of columns and rows that you have. So the lower it is, the less of a relationship you have. The higher it is, the more of a relationship there is between these variables. But it's not like the lowest is 0 and the highest is 1. I'm so sorry. The lowest and highest, what those are, it's going to depend on whether you've got a 2 by 2 table, a 3 by 3 table, or some other number of tables. Lower means no relationship. Higher means a stronger relationship between your independent and dependent variables. All right. Let me take a deep breath so I don't misspeak again. Okay, a third non-parametric statistic you might use is Cramer's V. You can use Cramer's V with any number of rows or columns. It is bounded by 0 and 1. So the lowest it could possibly be is 0, and the highest it could possibly be is 1. If the V statistic is close to 1, that is telling us that if we know the values of one of our variables, we can guess really closely what the other is likely to be. So if you do a Cramer's V test and that V is close to 1, that means if you tell me the independent variable value, you can also tell me with pretty reasonable accuracy the level or value of the dependent variable. Right? So this is about how accurate a prediction of one is going to be based on knowing the other. Okay. Those were all non-parametric tests for nominal variables. Here are some non-parametric tests for ordinal variables, and you can use one or more of these three if you've got ordinal variables. The first is gamma. The gamma statistic will range from -1 to 1, where 0 as the midpoint means there is no relationship between these two variables. So if you test the effect of x on y or the relationship between x and y, and your gamma statistic is 0, it means there's no relationship between these two variables. If it's -1, it means they are negatively perfectly related, meaning as one goes all the way up, the other goes all the way down, right? If the gamma statistic is +1, that means they are perfectly positively related. As one goes all the way up, the other goes all the way up. So gamma has the nice property of telling us not just whether the two variables are related to each other, but actually telling us the direction of the relationships. If one increases, if your independent variable goes up, does your dependent variable respond, yes or no? And in responding, does it go up or does it go down? Right? It's a really nice property of gamma. There's also Kendall's tau or tau, depending on how you pronounce that Greek letter. Either way, it's the same statistic. Kendall's tau ranges from -1 to 1. Again, 0 means no relationship. It's generally seen as a better test than gamma for a series of mathematical reasons I won't go into. With the tau-B test, your table has to be square. With the tau-C test, it does not. So if you have a square table and you want to run Kendall's tau, then you want to run Kendall's tau, the tau-B test. You'll find all of that stuff in Stata. If it is not a square table and you want to run Kendall's tau, you want to run the tau-C test. But again, interpret it the same way you do gamma. 0 means no relationship. -1 is a perfectly negative relationship. +1 is a perfectly positive relationship. The last non-parametric statistic for ordinal variables that I want to cover is Summers D. With Summers D, it doesn't matter what the size of your table is, but it is an asymmetric test. And so you do have to identify your dependent and independent variables. And again, you're looking for significance, statistical significance through a p-value. You're looking for negative, statistically significant results for a negative relationship. So one goes up, the other goes down. You're looking for positive statistical results for a positive relationship. So as one goes up, the other goes up. And 0 means no relationship between them. So that's chi-squared and its extensions. Those are the bivariate test statistics you would calculate in Stata. If you fit into that row of the table, what statistics do I use that I showed earlier? I'm going to pick up next time by talking about ANOVA and then about correlation. See you then.